What we're looking at now is sending random processes through linear systems. And we're starting with steady state analysis, which means out as time goes to infinity. And we went through and derived ways to characterize the output signal, which will also be a random process. So we're talking about a wide sense stationary random process input through a linear system that's stable. And it turns out the output is also wide sense stationary. And we have these ways to compute various characteristics of the output signal. The mean, the power spectral density, autocorrelation function, mean squared. So we'll take these, put these in our hip pocket. It's kind of a formula sheet. And now I'll do an example. Here's the physical process that's going on. We have this little circuit where the X is the input voltage, Y is the output voltage, and the input is this string of impulses that are randomly distributed in time according to a Poisson distribution. I think the average time between them is K units. Anyway, we'll take all this as a given. Actually coming up with these things is not all that easy. I think it's one of my homework assignments when I taught the class. But we can kind of ignore this physical process if you want and just say, okay, here's what we know. The input has this mean, this autocorrelation function, and the system has this transfer function. Our job is to find the steady state, mean, power spectral density, autocorrelation function, and mean square value. Well, the mean is easy enough. It had a fairly simple way to calculate it. G evaluate the transfer function evaluated at 0, which is just 1, times the mean of the input, which is K. So the mean of the output is just K. That was easy. To find the, well, what it was asked for, the power spectral density of the output. And we get that by, first we need the power spectral density of the input. And that is just the Fourier transform of the autocorrelation function, input's autocorrelation function. So we need a table for that. Dirac delta function is just a constant. When it's just a unit, it's just a 1. So that's a 1 times K. And a constant, Fourier transform of a constant is a Dirac delta function times 2 pi. So this is all from a Fourier transform table. Got the table, that's a fairly easy thing to look at. The formula is going to be, well, it's going to be this, or it's this times, well, we'll say it's this. There's the input power spectral density, output power spectral density, and we need this thing in between. There's 2 ways to calculate it. Here's one way. It's a complex number. Take the magnitude of it. Here's the transfer function. Plug in j omega for s. And the magnitude of a complex number is the imaginary part squared plus the real part squared. So here's what that is. Or if you calculate it this way, you'd end up with the same answer. So the output is going to be this times this, which is that. So that's the power spectral density of the output. Here it is again. To find the autocorrelation function, that's the inverse Fourier transform of the power spectral density. So let's rewrite it a little bit. break it up into terms, a k over this omega squared plus 1, and then this over omega squared plus 1. Well, this Dirac delta function is 0 when the argument is not 0, or when the argument is not 0. Which means I can just set this denominator to 1. Pull out a k over 2. No, just pull out the k squared, and I'm left with this. I could get rid of this omega squared again because this whole thing is 0 except when omega is 0. So the front part, I'll pull out a k over 2, so I get a part that matches the table. And in the Fourier table, there's a 2 pi Dirac delta function. So I'll pull out the k squared. So this is all just a table lookup thing. So it's k over 2 times e to the minus absolute value of tau plus k squared. Inverse Fourier transform of this is just 1. Anyway, here is the autocorrelation function of the output. The mean square is this guy evaluated at tau equals 0. That becomes a 1. I have a k over 2 plus k squared. That's the autocorrelation function. Excuse me, that's the mean square. Then the variance is the mean square minus the square of the mean. That's just k over 2. So look at all the things we found out about the output. Mean, power spectral density, autocorrelation function, mean square, variance. I'll save this second example for another video.